last Friday and just felt disgusting.
Okay. Oof.
A live rat.
So just a reminder that we have our exam review tonight, 5 to 7. I will send out a Zoom link at the time. And
I had a question. Is it going to be in person
It's
and streamed on Zoom, or is it going to be just?
it's just going to be from Zoom. So I will send a link and you can join. I expect you to bring questions. Okay, so that's what it's for, is to answer questions you have. So we have drafted the midterm at this point, and I can tell you the topics. So get out the pens and paper. So you're going to have to do via CPR and Lewis dot structures. You're going to have to make molecular orbital diagrams, and we're going to do pi effects. And so you should review the pi effects part of the MO diagram material that we've done, and we'll keep that relatively simple, but I'd like you to be able to go through the mechanics of doing pi effects. Okay. You need to know your periodic trends. We spent a lot of time talking about Z effective and how it varies and what properties that causes, like radius, for example, electronegativity. We talked about Bent's rule, the influence of electronegativity on geometry. Let's see here. You're going to need to assign point groups. There's going to be no flow chart. You're going to need to be able to just look at the molecule and guess the point group. If you need help with that, there's that link that Barrick had shared. And let's see here. I think that's everything.
What were the first 3 points you said?
I don't remember.
Okay, neither do I.
Yeah, that's right. Yeah. This will be posted online too, if you want to go back and look at it. Okay. Hopefully by this point, you feel comfortable generating a reducible representation by asking whether or not the ligands move, right? Or by looking at what happens to the central atom. And then breaking that down into irreducibles. Got to be able to do that. Yes?
Will the review session be recorded?
The review session will be recorded, yes. And I'll post it on YouTube so that you can look at it on your own time. And if you can't make it and you want to send me a question ahead of time or whatever, that's fine. Okay. Anybody have any questions? No?
No, covered up during the exam.
Oh, that's another important one. Good one. That's going to be covered, and you must know the. So you must. No, you must know the periodic table. You will not be given a periodic table, and in fact, you have to fill one out. Okay, so you must know the periodic table. That's the first question on the exam. So you just start by filling it in, and then you can work from it.
Do you do error carry forward for the periodic table, or is that?
What's that?
Do you do error carry forward for the periodic table?
I don't know what that means.
So like, let's say, you assume.
Oh, you get the
element
periodic
is
table
in the
wrong?
group. So because you labeled it on the periodic table, like does it carry forward?
Good question.
Because that's the biggest concern with the periodic table.
Well, we'll see what happens with your exam, okay? I'll have to think about that. You should know the periodic table. It's hard to participate in this class if you don't know the periodic table. Can you guys see? Sort of? Better? Thank you. Okay. So let's go back and finish our sigma plus pi picture for octahedral. I'm going to show you two different cases here. So for cobalt hexafluoride, we went through and generated our 6 ligand sigma. We did the gamma XYZ times 6 ligand sigma, and that gave us a little XYZ coordinate system on each of the fluorines. One of those vectors points at the metal. That's the same thing as 6 ligand sigma. And so if you subtract 6 ligand sigma from that gamma total, it leaves the other two behind. So that's how you generate the pi orbitals, right? That trick is pretty useful. It works when you have two lone pairs of pi symmetry on your ligand set. So we ended by comparing the sigma only picture and the sigma plus pi picture, where now we've got 6 ligand sigma on this side, we've got our metal in the middle, and we've got 6 ligand sigma plus 12 ligand pi over here. And because we're doing cobalt hexafluoride, I'm going to take 1, 2, 3, 4, 5 d orbitals on our metal center. And I'm going to take 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have the 6 ligand sigma part, and we have the 12 ligand pi part here. On this side, I'm just going to draw the 6 ligand sigma part. So these guys are going to make a bonding interaction. And the metal ends up with two different levels, where this is EG and this is T2G, right? So these guys here are non-bonding. They do not share any symmetry relationship with these 6 ligand sigma orbitals. These guys are anti-bonding with respect to the ligand orbitals. So down here, we're going to have the bonding part. This is the anti-bonding part. This is the thing that we care about, where this is our delta O spacing. So on this side now, we get the same thing for the sigma orbitals. These guys are sigma star. But then we also have these pi interactions, and the 6 ligand sigma here, this guy is A1G, EG, and T1U. This guy here is T2G, T2U, T1G, and T1U. Right? These orbitals here, the metal part is EG and T2G. So we're going to have the same thing up here. We've got our EG level going up. And this T2G level now is no longer non-bonding. It's going to be anti-bonding. Pi star. And that's because down here on the bottom, we're actually going to have two different pi symmetry interactions. We have a T2G1 and we have a T1U variety. And I haven't drawn the T1U orbitals on the metal. Those will be up here. Okay, I'm just talking about the d orbitals now. What orbitals are T1U on the metal? what kind of metal-based orbital has U symmetry? What's that? P orbitals do, right? An s orbital is symmetric with respect to inversion. A d orbital is symmetric with respect to inversion. A p orbital is anti-symmetric with respect to inversion. That means it's U. In octahedral, it's T1U. Okay, so we have some pi bonding with those 4p levels. Yeah.
I just said that it was doubly degenerate. Is T doubly degenerate or triply degenerate?
T is triply degenerate.
E is doubly.
Yeah, E is doubly degenerate. These guys are also pi bonding. Is it a little confusing that T1U is pi bonding and T2G is pi bonding? Anybody bothered by that? Yeah?
Is it because of like orbital overlap or?
Well, yeah, I mean, the question is a question about symmetry, right? So what kind of orbital has G symmetry that makes a pi bond? The D's do, right? This p orbital symmetry also makes a pi bond. There's two different types of pi bonds, one with the p's and one with the g's. There's the T2G antibonding. These guys come from the metal d orbitals. Okay. So we've drawn those souths out previously. What d orbitals have this symmetry and are antibonding with respect to the fluorine lone pairs? Yeah. There's two sets to worry about in octahedral. There are the ones that point at the ligands and the ones that point in between the ligands. What are the ones that point in the ligands in octahedral? dz squared and x squared minus y squared. The squared ones point at the ligands. The other three point between the ligands. When you point the lobes between the ligands, you end up with something that has pi symmetry here at the orbital. What's that? dz squared and x squared minus y squared point at the ligands. dz squared and x squared minus y squared point at the ligands. Got to remember that. Yeah, these three here are the xz, yz, and xy. Yeah. All right. So this diagram was drawn carefully enough to illustrate the fact that the pi star interaction here with the lone pairs on the fluorines pushes this level up and shrinks delta O. Let's do this again, but this time we're going to do it with a pi acceptor. Okay, so this is now the okay, so I'm going to skip the sigma only. I'm just going to do the metal-based orbitals here. We got 1, 2, 3, 4, 5, e.g. T2G again. And let's use carbon monoxide. But you could do the same diagram with PF3 ligands, for example. And we're going to put down here 1, 2, 3, 4, 5, 6 ligand sigma orbitals. Same symmetry, we're in octahedral here. So these guys are going to be A1G, yeah, T1U and EG. But if we're doing carbon monoxide or PF3, where do the 12 ligand pi orbitals go? above the metal, right? I thought the ligands were always below the metal. These are antibonding levels we're talking about. These are the pi star orbitals on the CO. So those empty orbitals show up here. And we could even call them pi stars if you want. Okay. Normally we just say 12 ligand pi, but this is a pi star orbital on carbon monoxide. So we're going to start it above the metal.
And it has to do with the other out is pulling, the pi acceptor is pulling the bonds closer together. It's making the metal and the ligand closer, so the energy is raising on the ligand. But does that lower the energy of the metal?
What you said is very true. And we're going to do that in just a second. To begin with, we're just drawing the CO fragment. Okay. If you were to do a molecular orbital diagram for carbon monoxide, you'd end up with pi symmetry orbitals up here and sigma symmetry orbitals up here. Right? These are antibonding levels on the ligand. We're going to mix those with the metal. We're in the same situation here. We've got a T1G, a T1U, a T2G, a T2U. You know, it's the same symmetry problem as it was before. And now we got to put these things together. So we're going to have 1, 2, EG sigma star, just like we do up there. But now the T2G level here can interact with this T2G level, right? So what's going to happen is that it's going to go down, and it's pi bonding in this case, and the T2G level goes up here, and it's pi star. There's also a, sorry, I should have done it like this. There's also a pi star level up there for T1U. We're not drawing the 4p orbitals on this diagram because I'm really only interested in the d orbitals for this discussion, but they would be part of the mix, okay? And then of course there's the 1, 2, 3, 4, 5, 6, 1, 2, 3, oh, sorry. I'm going to call them non-bonding. They started off pi star orbitals on the CO, okay? So it's a little bit tricky to say, hey, these are non-bonding. The point is that they're non-bonding with respect to the metal. The metal doesn't have the symmetry needed to make a connection here. And which ones are those? T1G, T2U. Okay, those things do not have the same symmetry as any metal-based orbital. Margo.
Just to clarify, the atomic orbitals on the metal that have the lowercase Mulliken symbols and the same on the ligand, are those supposed to be like that, or are they supposed to be uppercase?
These should be uppercase, sorry. Typically, I try and write the Mulliken symbols of the atomic orbitals in uppercase and the molecular orbitals in lowercase. I don't know, I'm kind of being sloppy here. Excuse me.
It doesn't make a difference, right?
It does.
Oh, it doesn't mean something entirely else. Okay.
Well, I mean, I think it's important to be rigorous in your representations, you know. So let's do that. Let's be rigorous. You know, I mean, I think also this is a little confusing, right? Because we're taking what is really actually a molecular orbital on this side and mixing it with an atomic orbital. So that's part of the reason I chose to write those as lowercase here. But over here, anyway, I think that you get the point. The important aspect of this diagram that I'm trying to highlight is that because these things are accepting and above the metal. Now the thing that looks like the metal is the bonding half, okay? And this makes sense from an electrostatic picture. Why does it make sense from an electrostatic picture?
I don't know if this is right. I think it's because the parentage of those orbitals is lower in energy. So they're more stable, so they're not anti-bonding, it's not as much. All the anti-bonding orbitals are fire energy. Right, they're out of phase, maybe of the same symmetry. They are the same symmetry. Those are in phase and the same symmetry. They have better overlap. They're more stable. That's the only way I can read it.
Yeah, well, I mean, what you're saying is all true. You know, I think the nature of the question is that, do you want to give it a shot?
Yeah, I was just gonna, is it not just because the metal is the one donating the electrons back into the fire?
Okay, but what does that have to do with this orbital dropping down? I think you have the right idea, but why did, I told you that this level is dropping down in this case, and I want you to say why that makes sense from an electrostatic point of view.
Because it's farther away. Yeah, because it was concentrated around a lower electronegativity atom, right? The metal doesn't want the electron that much, but then once the ligand pulls it a little bit more, there's two things pulling on it, so it stabilizes that.
Yeah, okay, so I think you basically have the idea. I'm gonna ask a slightly different question. The question is, what type of an orbital is this? I've labeled it pi here, but if I pointed this on the exam and I said, you know, what kind of an orbital is it? Who does it belong to? What are the coefficients on the atomic functions like? Which orbitals, if you had to label it as a kind of an orbital I'm familiar with, what type of an orbital would you call it? A d orbital. Why would you say that?
It's closer to the metal atomic orbital than it is to the orbital.
Yeah. The parentage of the orbital we're interested in is related to the orbitals that it's made up of. And one way to think about this is that this is a d orbital on the metal. And it's stabilized by the ligand pi star, because the ligand pi star is an acid, it's positively charged. And that connection between any electrons on this d orbital and that positively charged thing will stabilize the electrons in the d orbital. So we're saying that this is like a d orbital on the metal. And these 5 levels here, these are the frontier orbitals, right? We talk about this 5 set of levels like they are the d orbitals on the metal. So now, this is like a d orbital on the metal. Why does its dropping here as opposed to raising there make sense from an electrostatic point of view? And let's put electrons, let's pretend there are some electrons in this level. Okay, Margot, you want to give it a try?
Sure. I was sort of thinking about it as there's now like more room for the electron to be in, because it can also be in the pi star orbital, so it can sort of find its place better, and therefore the whole system is more stable.
Delocalized, maybe.
More delocalized, more room to distance itself from things it doesn't like, therefore more stable.
Right. And how about in that case?
There it's closer together, so it's less stable. Or it doesn't have that interaction with the pi star.
What's its interaction like instead?
It's accepting more electron density from the pi donor.
Yeah, or I like the case of, you know, hydrazine versus ammonia. You look at the lone pair on ammonia, and then you compare it to a lone pair on a hydrazine. The lone pair on a hydrazine has got another lone pair next to it. And those two are interacting with each other in a way that makes for a much more energetic molecule. When you have 2 sources of electron density interacting with each other, the density is greater. And it becomes much easier to pull an electron out of that situation. You know, if I hand you a box with 1 electron in it, and I hand you another box with 1 billion electrons in it, guess which one it's easier to get the electron out of, right? So here we've got electron pair interaction. That raises the electrons in energy, pushes them closer to vacuum. If you drive a lot of charge in there, eventually electrons are just going to go flying out into vacuum. In this case, we're taking an empty orbital here. A pi acid. What is an acid? An acid is a source of positive charge. You stick a positive charge onto a negative charge and you stabilize it. And that's what we've done. We've taken a source of negative charge, which is the d electrons. We've put this pi acid on there and those d electrons dropped, right? Because this is like the d orbitals. Well, that's the electrostatic picture. You take 2 electron pairs, you force them on top of each other, it becomes easy to pull an electron out. It's like a fight, right? Coulombic battle. That's what's going on up there. Here, we've got a marriage of plus and minus. And we're paying attention to what happens to the d orbitals because that defines the behavior of the compound. Okay? Go ahead.
So like the T2G from the metal in this pi acceptor version, there's this interaction with the p sigma star, and it's stabilized by this electrostatic interaction, which basically means its electron density lower picture is higher than the one at the top.
So we're mixing it together with an empty pi star orbital, and that electrostatically stabilizes the d electrons.
It's like the electron density is a little lower.
Yeah, or in the top version, we take electrons on the metal and electrons on the ligand. We put them on top of each other. You get a bonding orbital and you get an anti-bonding orbital. The anti-bonding orbital happens to be the d electrons. So the d electrons that are sitting on the metal, you start forcing ligand electrons up against them, it pushes them up. Let's say the metal had sigma only ligands for a second, but it was all of the d orbitals were filled with electrons. You start bringing up Lewis bases, sigma donors, you're going to pump up the electron energy on the metal. You'll force that sigma donor right into a d orbital that's filled, and there's a problem, right? You don't take a filled thing and stick it to a filled thing. So that raises the energy of the electrons that are sitting in that level by bringing up more electrons and shoving it in its face, right? The antibonding level shows the electrons raising in energy.
There's more repulsion in the pi donor.
There's repulsion in the pi donor case, that's right.
Just want to go back to my just to make sure I understand. It's kind of the same question. This is the pi acceptor. There's a plus charge on it. Okay, I have a metal. And so when you mix the orbitals, the energy for the T2G, the DO for the T2G, the EG star is going to increase because the electron density is able to flow. There's not as much, like you said, Coulombic force. And you're saying it's easier to pull an electron out when you have a sigma donor, like we're donating electrons with a ligand to the metal. You're saying the electron that's easier to pick off is from the molecule, not the atomic orbitals.
Well, yeah, it's the molecule I'm interested in, but we're talking about the parentage of the orbital from which the electron comes.
Right. So T2G is more like a d orbital. And so the metal is a d orbital, we know for sure. The sigma ligand pi has d orbital symmetry. Right?
Has pi symmetry.
It has pi symmetry that can bond with the d orbital. But T2G is actually the d orbital. The energy which is closer to it is the metal.
Right, yeah. The coefficient of the d orbital atomic orbital part of the LCAO, the linear combination, the coefficient in front of the d orbital is the largest. It's most like a d orbital. If you were to plot it out, calculate with density functional theory, you'd see a big fat d orbital and a little bit of ligand contribution.
And so the DO is just showing us that it's more stable as you increase the DO between the T2G pi and the sigma star EG. It's showing that the effect of the pi accepting ligand is giving it, it's just, why it's harder because it's more stable. Because the electrons can leave, there's less coulombic force. So to remove an electron from the molecule, it is more difficult.
Yeah,
Okay, I understand.
yeah.
Sorry.
the ligands are positively charged in this sense. There's no formal positive charge here. We're just talking about this pi accepting piece. You know that carbon monoxide is hypovalent, right? It wants electrons. And what is the orbital it uses to want the electrons most? The pi star. Okay. D orbitals on a transition metal have the right symmetry to make a connection to those empty levels. So the electrons can delocalize into them. They get stabilized as a result. If instead you surround the thing with pi donors, those poor D electrons now are in a battle and they get pumped up in energy. All right, so pi donors. Ooh, we've got our EG level here, which is sigma star. We've got our pi star level here, which is T2G. Have a little delta O. We've got sigma only. And then sigma only, it's non-bonding. And we've got sigma, sorry, we've got pi acceptors. Okay. So that spacing has a really big impact on the molecule's properties, which we're going to spend some time talking about. One of the things it does is it changes the color of the compound. When you have small gaps like that, you have low energy absorptions. When you have big gaps, you have high energy absorptions, right?
Is that related to the color of the complex?
Yeah,
Oh,
yeah,
I vaguely remember.
yeah. Yeah, we'll do some more examples of that. I need to get my act together and actually bring some of these compounds in so you can see them. You know, transition metal complexes are beautifully colored. And the classic ones, the salts that geologists and early inorganic chemists studied, all the color came from those gaps. All right. So this relationship is pretty rock solid. Okay, sigma and pi changing the splitting of the D levels, and inorganic chemists spent a long time charting that all out. And so people have learned to understand different kinds of ligands in this context. And in particular, the magnitude of delta O and the ligand type has been related. So I'm going to show you a bunch of different values of delta O here qualitatively to show the ligand type. Okay. So as we go from left to right here, the delta O is shrinking. So if I were to bring in a bunch of compounds that had these types of ligands on them, the molecules on the left would be maybe pale yellow or colorless. The molecules on the right are more likely to be green, red, blue and purple. So these guys here are considered pi acceptors, and people call them strong field ligands. Okay. What does that mean, strong field? What's the field a reference to? It's a reference to crystal field theory. Okay. The crystal field is the negative charge surrounding the cationic metal. And in this case, it's not just a negative charge, it's a mixture of negative and positive charges. And that field splits the d orbitals. So the magnitude of the field is largest when you have this type. And over here, these guys, it turns out, really, these are sigma only ligands. Now you might say, well, wait a minute, water has an extra lone pair. Probably got some pi effects. But water is such a weak pi donor, people just say it's sigma only. These ones over here are pi donors, and people call them weak field. Okay. Now, how about the difference between water and ammonia? Is this because of pi effects? Water's kind of it's basically sigma only, okay? But why is ammonia to the left of water on this chart?
I think nitrogen is less electronegative, so it's not as character.
If I gave you a glass of ammonia and a glass of water, which one would you rather drink? Glass of water. Why is that? Because ammonia is going to burn you if you try and take a drink of it. Why is that? Because it's basic, right? It's a much more potent donor than water is. So why does that change the ligand field strength?
Sigma star is going to go up by a few points.
Yeah, when you're more potent donor, the splitting is larger. Sigma star is higher. If I were to say, all right, I've got a metal metal ammonia bond and a metal water bond, and I want you to put an electron into the empty orbital on that metal, the sigma star level, which one is better at accepting that electron? It's the one that has the weaker donor, because that extra electron can sort of it's easier to duke it out with water than it is to duke it out with ammonia, because ammonia is a more potent donor, more electron releasing. So the empty orbital on the metal is less accommodating to an additional electron. All right, so that these effects here have both the strength of the pi acid character. Look at this electronegative thing, nitrosonium over here, right? Cationic, 2 electronegative elements. This has the same, it's said to be isolobal with carbon monoxide. So it has the same symmetry, pi star levels, sigma donating levels. These two guys way down here on the left, very, very strong pi acceptor in this case. So the strength of the interaction is part of the story here.
Well, that's like monoxide is so poisonous, right?
Oh yeah.
So,
Well, carbon monoxide is poisonous because it sticks to your hemoglobin, and then you cannot bind oxygen anymore. Just like cyanide. Everybody worries about cyanide poisoning, but CO is just as bad. All right, let's see here. So this is really important. Now, wait a second, did I lose this thing? Why is that sitting in here? Okay. All right, so let's use some of this information and look at real compounds for a second. Or for a second, for the rest of the class. So let's do some periodic trends. For transition metal compounds. You know, you can get a whole variety of different things depending upon your ligands and whatever. And one of the things that you'll find is that Z here is basically always between plus and minus 4. You never really go outside of 4. Usually 4 is unusual. 3 is not too uncommon. So let's talk about something called the oxidation state. You guys know about this already. Oxidation states of the metal, they go up as you go left to right, beginning up until group 7. Okay, so start over there at scandium. You know, it's not hard to get rid of all the electrons off of scandium because of how electropositive it is. But as you go to the right, you add more electrons and the metal gets more electronegative. Okay, so there's more electrons to pull off. Say vanadium, you know, you got 5 to start with. You can take all 5 electrons off, but once you get to iron, you have 8 electrons. The metal is more electronegative and it gets harder to pull off 6 electrons. Okay. So then the oxidation states tend to go down. Nickel, palladium, platinum, they like to be metal 0 because they're electronegative. They're kind of like noble gases in a way. It's hard to pull all the electrons off of the nickel, or palladium, or platinum. And so you don't get to oxidation states greater than 4 for the most part. Oxidation states go up until about manganese, and then to the right of that, they tend to go back down. So oxidation states tend to go up as you go down. Cobalt, rhodium, iridium. Down at iridium, you can go to iridium 5. Cobalt doesn't make 5+. Osmium and iron have a similar relationship. So you're much more likely to form lower valent oxidation states at the top of the 3D metals than you are with the 5D metals. So titanium is often titanium 3, occasionally titanium 2. You don't do that as easily with hafnium. Let's see here. Coordination numbers of the metals go down as you go from left to right. Why would that be? The electron count is going up. Why does that matter?
Less empty.
Why does that matter? You're saying the right thing. I just want you to be more explicit. So electron counts going up, so you have fewer empty orbitals, but why does that mean that the coordination number changes?
Then you have less d orbitals for ligands to donate.
Yeah, and ligands are primarily bases, right? Ligands are donors, metals are acceptors. You need an empty orbital on the metal to accept electrons, and you fill the metal up with electrons and it cannot accept the donor anymore. And then finally, you're already familiar with this one. Metal ligand bond strength goes up as you go down. And I think the best explanation for this, or the one that is most intuitive to me, is that because of the lanthanide series filling, the effective nuclear charge is unusually high, and the 6s orbital is unusually low, so it's more relevant for bonding in that transition metal. That's the main reason. Okay, so let's see here. Yeah. Let's look at some example compounds.
Before that series in group 6, like when we're between the lanthanide, would the bond strength still go up as you go down?
The bond strengths
Above the,
between 3D and 4D,
yeah,
they still go up, yeah.
okay. Is there an explanation for that?
I don't think there's a great one, no. I don't think that there's a great one. Some of it has to do with the spin states that tend to form. Bond strength is a complicated collection of, there's a lot of things that contribute to bond strength. All right, so let's do some example compounds here. We've already talked about this one. Titanium hexaquo 3+ ion. How many d electrons does titanium hexaquo 3+ ion have? Well, you already know water is just a simple neutral ligand, right? So if this thing is 3+ overall, that means the titanium must be 3+. And how many did it start with? Titanium, zirconium, and hafnium have 4. So this thing is D1. Just make sure we're doing this over. It's not. Okay. Just make sure everything is hunky-dory so everybody can hear me. I'll just check and see. Can somebody out there give me a thumbs up or let me know that everything is working on the Zoom? Can you guys hear me? Doesn't seem like it. Oh, yes, good. Okay, all right. Thanks, guys. No, that's not what I wanted to do. There we go. Okay. So this thing is D1. Let's draw out its splitting diagram. 1d electron. And people label this compound with a term symbol T2. What does that mean? It means that this is a doublet. Okay, the spin state of this compound is a doublet. What's a doublet? A doublet is 1 electron. Maybe you remember singlet and triplet, right? A singlet is no unpaired spins. A triplet is 2 unpaired spins. So it's 1 more. So doublet for 1 unpaired electron. Okay, and it's given the symbol T. What do you think the T means? It means there are 3 equivalent places you can put that electron. So this spin state is triply degenerate as a multiplicity of 3. With the triplet, it's a doublet T term symbol. So it just makes it easy to refer to the electronic state of the compound with this nomenclature. Let's do another one. Do vanadium hexaquo. Also 3+. On the electrons, on the metal, vanadium is 1 to the right of titanium. So that means it started with 5, 3+ leaves 2d electrons behind. Hund says, put them in separate orbitals to get the best exchange and the best Coulombic situation. 2 unpaired spins is a what kind of state? Triplet state. What is the degeneracy of this state? How did you know that? Or how would you explain that to somebody that said, wait, why is it 3?
Well, there's one with no electron attaching the any one of the 3, so there's 3 options.
Yeah, count what happens to the hole. The hole can be here, here, or here. Okay, so this is a triplet T term symbol.
Can I ask a question?
Yeah,
If you have one, so because of Hund's rule, we're always gonna put, never gonna have 2 electrons in the flow, still do at least 1 ion, right?
yeah,
Yeah, so it can't be like if there were electrons in those orbitals, it still would be, even though that can't happen, it still would be triply degenerate.
yeah, we'll do that case in a second. Okay, triplet T for vanadium hexaquo. Chromium hexaquo. How many d electrons? Chromium is another one to the right. Chromium, molybdenum, and tungsten start with 6, so 3 plus ion is D3. Hund says it's a quartet because there are 3 unpaired spins. What's the degeneracy of this thing? Or multiplicity? Degeneracy, not multiplicity. There's no other way to write this thing, okay? So this is A. So same situation for the group theory. It's an A. A means singly degenerate.
Wait, it's just a common in A,
What's that?
there's no 4, or what's that?
That's a quartet for A, yeah. All right. Manganese 3 plus D4 starts with 7. Manganese is 1 to the left of the iron column. Technetium and rhenium are also in manganese's column. Starts with 7, 3 plus leaves 4 behind. Ground state in this case is what? It's a triply degenerate triplet. 2 unpaired spins. You can take this 1 down electron and put it here or here. Okay, so there's 3 ways to write it. This is a triplet T. But you might say, well, wait a minute. I know this compound is not a triplet T. What's another possibility? Something called the high spin state, which looks like this.
It looks like it could be more stable, based on Hund's rule on the orb, the spin.
Yeah, sort of. So it looks good from Hund's rules point of view, but you need to calculate the energy splitting of that gap to know whether this is true. Because you had to push the electron up to get that exchange and to eliminate the Coulomb repulsion. So you have to jump across the gap to do that.
Because it's sigma only and that's gonna be an anti-bonding orbital, does that make it a little, like, does that make the bonds a little less, like a little more weak? In any sense?
Yes.
And, okay,
Yeah.
that makes sense.
Yeah. Yeah. So let's finish the discussion here of the term symbol. So this guy, we have 4 unpaired electrons. That's a quintet. And what is the degeneracy of this quintet? Doubly degenerate, because you can put the electron on the left or the right. So this guy is a quintet E. 'cause E means doubly degenerate, right? So it turns out this one is the ground state. Interestingly, this compound can absorb a photon to drive the electron down here. That's very improbable because there's a couple of problems with that. You have to change the spin state, and that generally doesn't happen when you do a photon absorption, and you're doing a D to D transition. That's not allowed. But it still happens a little bit, very rarely, but sometimes. Photon absorption can cause the electron to go down. It's kind of cool. This thing here is called the high spin state. This one is called the low spin state. And the magnitude of that delta O determines whether it's high spin or low spin, as does the number of electrons involved in this, in the two. All right. So promoting an electron here exceeds the pairing energy, and so it's favorable to make the high spin compound. So the pairing energy what is the pairing energy? Pairing energy is this Coulomb plus exchange thing. Thank you. I've always found that so strange. Why do people say bless you when you sneeze?
My mom,
I'm worried for your health. Is that a question?
Yeah.
well, my mom used to tell me that your heart stops when you sneeze, and I don't know how true it is, but I feel like it's kind of sweet, like, oh, you're back.
That is sweet, yeah.
Historically speaking, I think people thought you were being possessed by the devil every time you sneezed, so they would say bless you.
I didn't hear that, I'm sorry.
People thought you were being possessed by the devil. So they would say bless you.
Yeah. Bizarre.
I like my mom's.
Yeah.
I don't agree with any of the superstition. At this point, I'm just being polite.
Right, well, but why is it polite?
It's not even comfortable to sneeze,
Like wear pants, we just kind of do.
I kind of like sneezing. All right, so the pairing energy for manganese 3 plus is 28,000. It's kind of interesting, right? That you can just name a pairing energy for a 3 plus ion like that. And it's, you know, probably it's only really an octahedral, but there's only 4 electrons and you got 5 spaces to put them. So you can count the number of unpaired spins.
What unit is it?
I'm sorry?
What unit is it?
Oh, sorry. Wave numbers, inverse centimeters. Well, delta O. So the spacing, the delta O here is only 21,000 inverse centimeters.
That makes sense.
Okay, so you gain 7,000, or the difference in energy between those two states then is the difference between those two numbers. It costs less energy to promote an electron, 21,000 wave numbers, than it does to pair them, to disobey Hund. Yeah. This isn't technically a Hund situation because they're not all at the same energy level, but anyway, go ahead.
So does that mean that you could emit a photon by promoting it?
Yes. Of 7,000 wave numbers, yeah, and that happens. And those are like common transitions and transition metal ions stoked in the crystals. You see that type of thing. Yeah, it feels strange, right? You're used to seeing an electron go up in energy when you excite it. This is an excitation that involves an electron going down in energy.
I mean, I feel like math makes sense in a way, like if you have like a darker colored metal and it makes a really bright complex, like that some energy is being emitted in that. Is the photons.
Yeah, it's really the issue is the correlation between the ionization potential and the excitation. All right, so let me see here. What am I doing? Okay, so this type of a situation where you've got different spin states is really common in the transition metals. And there's some rules of thumb about how to estimate what's going on, what kind of a spin state you can expect. All right, so there's sort of three situations that we're going to talk about. Third row transition metals that are octahedral, they have pairing energies greater than delta O in some cases. Let's see here. Third row. So the 3D metals, sorry, not first row, third row, first row, transition metals, the 3D metals. Why does it say that? So octahedral complexes, the pairing energies vary. Depending upon the types of ligands and how many electrons. They vary from about 15,000 to 25,000. Delta O can take many different values depending upon whether the ligands are donors or acceptors or whatever. We talked about all those cases. Okay. There's a pretty big range in delta O. So the range of delta O can be larger than the range of the pairing energy. So the result is that you get spin states all over the place, depending upon what the supporting ligands are.
Are there high or low spin state depending on like just all the factors?
Depending upon the ligand field strength and how many electrons we're talking about. Okay, another situation are tetrahedral compounds. Tetrahedral complexes are different. They're almost always high spin. One of Jonas Peters' most significant compounds when he was first starting as a young professor at Caltech was a low spin tetrahedral cobalt iodide. And he presented it after it had been published in a sort of no-name journal. And Harry Gray, like the godfather of inorganic chemistry, said, "There's no way that compound is low spin." And Jonas was kind of like, "Well, what's the big deal? I don't get it." Tetrahedral compounds are almost always high spin when you're talking about first row transition metals. Why is that?
Oh, are we still talking about first row transition metals? Or
Yes.
is it just the general statement?
Well, especially for first row transition metals, this is true. And tetrahedral compounds in the bottom of in the 5D metals are not that common. I mean, they do form, but it's really the 3D metals that we're interested in, as you'll see in a minute, actually. All right, so they're almost always high spin. They have a splitting that is like this. It's T2 over E, okay? And T2 is the sigma star level here, and E is the pi level. So if we just consider sigma only for a second, you've got 3 d orbitals on the metal interacting with 4 ligands. Whereas in the octahedral case, you've got 6 ligands around 2 d orbitals. Okay, so the d orbitals don't get perturbed as much in a tetrahedral compound as they do in an octahedral one. So the TD splitting, delta TD, is approximately delta O divided by 2. So tetrahedral splittings tend to be small compared to octahedral splittings. Okay. All right.
What does that say?
Delta TD is about half of delta O. What's delta TD? It's like the octahedral splitting, but we're talking about tetrahedral compounds now. So it's the difference between, in a sigma only picture, that sigma antibonding level and the non-bonding level beneath it. All right, and the third situation is 4D and 5D transition metals. These guys are almost always low spin. Okay. They have pairing energies that are smaller. Okay. So their pairing energies are about 8,000 to 9,000 inverse centimeters. The electrons in a 5D metal are a little more diffuse. They're in bigger orbitals, and that makes their electron-electron interactions weaker. So that makes the pairing energy smaller. That's kind of an interesting thought. The electrons, because they're less local, they're sort of bigger, their interactions are a little weaker. There's more space for the electrons to go. The probability of their interaction goes down.
What does that 4 plus 5D and
4D and 5D transition metals in octahedral.
Oh, I thought it said Tim.
Sorry,
I was
I'm
like,
getting a little sloppy here.
no, it's all good. It's all good.
Oh, crikey. There's another effect you have to worry about when you go down. You get to heavier elements, and something called spin-orbit coupling turns on. And when you have spin and orbit coupling, it reduces the I think it also impacts the pairing energy. And the final thing is that delta O goes up, right? The strength of the bonding increases as you go down the period. And so delta O gets larger. So they're almost always low spin. You can basically just assume they're going to be low spin, but not every time. All right. So we're going to do some examples of that next time. I'm not going to try and chug through all these now. But part of the reason we worked up to this thing is to show you how the ligands can impact that splitting, right? You now know about sigma donating, causing the sigma star levels to move around, you know about pi accepting and pi donating ligand causing the other one to move around. And so now things like that series of ligand fields that we've shown you, hopefully will be very intuitive and will help you understand this stuff about what kind of spin state you get. And then later we'll do color, we'll do things like ligand exchange reactivity, all kinds of wonderful chemistry of the metals, totally determined by that orbital interaction. Go ahead, Ethan.
So say for example, the 3D optic references, is there a way to like reliably predict whether the high spin or the low spin, or is it just like external?
You can predict based on how many unpaired electrons there are and the strength of the ligand field. So ligands that have a strong field, those that are good sigma donors, which raise the sigma star level, and those that are good pi acceptors, which lower the other one, that gives rise to large delta O and low spin compounds. If you have pi donors that are kind of weak sigma donors, like halides, that gives you small splittings. You're more likely to get high spin compounds, especially when the number of potential unpaired electrons is high. Like manganese loves to be high spin because it's often 2+ and you've got 5 unpaired electrons. Pretty hard to beat that energy.
Okay,
So-
you can correlate this like the curve we talked about earlier.
Yeah. You get used to the various situations and guessing. So you can usually make a pretty good guess as to what the steady state is. Some of them are sort of on the cusp. Some compounds are so close that they interconvert. You can heat it up and it'll go to the higher state. You can cool it down, it'll go to the lower state. And that makes it a magnet that's temperature sensitive, which is cool. Yeah.
And I'm assuming all this, we can like hard compute and predict reliably. Just like with like just process all the geometry, everything and all the values and energy.
Can you compute it? You mean using like density functional theory or something like that, or?
And then just make predictions based on it. Like, are those predictions accurate? Is that like a thing that we're pretty sure of?
Yeah, so I mean, there's a huge history of the study of this stuff. There are thousands of compounds, millions of compounds that have been made and characterized. So there's a lot of intuition about how it works. Turns out that electronic structure calculations of this kind are really hard to do.
Yeah, I would assume it would take a lot of computation.
Computers are not very good at determining the difference between an energy of 2 different spin states. And a lot of interesting reactions involve changes in spin state, and you can't really compute the energy profiles very well at all.
Is there a reason for that, or?
It's hard to compute electron-electron interaction energies. I don't know the details very well.
There's something I was curious about.
Yeah, it's still a frontier. All right, happy to take 1 or 2 more questions. I have to run now, but exam is on Wednesday. I will see you tonight at 5 to 7 if you can make it. Recording of the lecture today and the review session will be on YouTube. All right, see ya.